Right. Okay. Hello, everyone. Thank you for coming to this presentation. So, I'm Kostas. I'm a lecturer in experimental fluid mechanics at the Department of Aeronautics. And I'll discuss today part of my work that has to do with modeling of wind turbines. So the title is Modeling the Aerodynamics of High Velocity Wind Turbines. And this work started during my postdoctoral appointment at Princeton, where I started with the modeling experiments, and then I continued here when I came out Imperial, initially as Imperial College Research Fellow and then as a lecturer. Okay, so this is just the outline of the talk. So first I will talk about the motivation behind these high volume turbines and the argument for wind energy in general. And then I will discuss how there is a gap, let's say, in the literature, in the modeling literature, where we can adequately model turbines that are of low solidity or low loading, but when we go to higher loadings, then there is a gap, and this stems essentially from the so-called Rankine Froude theory, which is the basis of most aerodynamic models that we use, also in industrial applications as well. So I will discuss a revision of that. And then I will apply this revision in 3 applications of engineering wind turbine models. And then I will conclude this talk. So the motivation, of course, is the huge expansion that we have seen in wind turbines and wind energy. So this is the installed capacity in kilowatts globally, right? Starting from the early 2000s until now. And you can see that the growth is almost exponential, right? And this is just from statistical data. And this of course does not stop here. You can see here that these are the historical data, but these are the projections. And you can see that the projected curve is almost exponential. And we end up at 2050 with an almost tenfold increase of installed wind turbine capacity, at least this estimation compared to now. But the question is what happens to 2050 and why do we need all of the energy? Well, there is this policy of net zero, so we have the UK, but in the European Union as well, and in the US and China, it's a global effort. And the effort is about trying to minimize the emission of greenhouse gases. So, for example, this is the emissions of CO2, gigawatts of CO2 on a global scale, and from different sectors, from power or from the energy industry, and different sectors. We are mostly in the context of wind energy, about the power and energy industry sectors. You can see that these are historical data, and these are projections. You can see that we have essentially 2 lines. One that is the dashed line here, which shows the net zero growth, where in 2050 we hope that we will have a zero of the emissions of CO2 and other pollutants. But this is a more conservative approach, and of course it will follow that. The price we'll have to pay is an increase, of course, in global temperature. Right? And then the question is, how are we going to achieve that? How are we going to minimize our emissions? And one of the solutions, not the only one, but one of them, is of course wind energy, expansion of wind energy. And how are we going to do that? Well, of course, what has been happening until now is, first of all, we increase the size of the wind turbines, right? So back in the 80s, when we started, even before that, with the oil crisis, heavily investigating research in wind turbines, we started with these quite small wind turbines here, but very quickly they increased in size, and right now we have this monster here of 200 meters in diameter. The motivation, the incentive behind that is because according at least to the Rankine Froude theory, it's not the only thing, but we expect that the power is proportional to the surface area of this here, right? And the higher surface area means we will have higher power extraction capability. So there is a huge incentive here. But apart from increasing the size of the wind turbines, what we can also do is increasing the number of wind turbines itself. So we cluster here in the wind farm. This is an aerial photograph from the Werle wind farm, and it's quite interesting because of the severe condensation. Right? The part is the wheel, and you can see it's a visualization essentially of the wake and how the wake of one wind turbine falls on the following one. And this is something that we'll discuss later on. But I mean, we have this clustering, and apart from that, apart from putting several wind turbines together, we start putting several wind farms together, right? So this is just a plan of the existing and planned wind farms in the North Sea. The green ones are actually the ones that already exist, and the purple ones the orange ones are currently under construction. The purple ones here are the ones that are shortly, the construction will shortly start. And here are the gray ones that are ones that are at very early stages of planning. So by 2050, we expect that all of these will be operational, and perhaps quite a few more that there are not even ideas now. So we see here that we will have a clustering not only of wind turbines, but of wind farms as well. So a lot of aerodynamic challenges here, and we need to actually solve that. It's there are a lot of design challenges as well. But apart from these gigantic wind turbines, the solution does not come from like only big sites, but comes from urban settings as well. For example, we can have micro turbines that, contrary to what we said before, where a whole wind farm could power a whole city or a whole sector of city. Here we'll have each wind turbine powering part or of the whole power consumption of the home, right? And you can see that because of the particularities of this problem, we have designs which are different compared to what we had before, right? We have multiple blades, 5 blades here, right? Or we have, whereas the conventional ones we probably know is 3-bladed turbines, right? And also we have solidities, so the number of the proportion of solid area compared to the disk here is much greater compared to the large wind turbines in the field. And this is for various reasons. One of them is that these turbines cannot easily self-start, right? So in urban setting, we have velocity fluctuations. The torques are much lower compared to the torque in the field of gigantic turbines. So the solution is sometimes to increase the solidity. But what I want to basically show here is that we have a very big variation in sizes, right? Starting from half meter or 1 meter diameter to essentially some centimeters in some more smaller applications. And then when we're trying to power up, homes in urban settings individually, we might end up with completely different designs. So we move away from the horizontal axis wind turbine, horizontal because the sense of rotation is parallel to the inlet velocity. So we can go to vertical axis wind turbines here, where the sense of rotation is perpendicular, right? So it's vertical axis turbines. And you can see that this is a completely different operational principle, let's say. And for example, here this is in a highway, and the idea is that as the cars pass, they will use the shear to generate it. So it's a kind of recycling of the lost power from the cars via wind energy principles. All right. So I mean, a very big diversity of design challenges, and the question is how how can we estimate, first of all, the power efficiency of all these things? How can we estimate the difference in power production from one to the other, right? Now, since the 70s, the idea is that most of the scientific community concluded that the horizontal axis wind turbines are the most efficient, right? And this is because individually it was quickly shown, but they produce much higher power. However, what has been recently been done is that we now start clustering wind turbines together in a wind farm, right? And as we discussed before, when we saw the area photograph from the Horn Rev, what happens is that the wake of one wind turbine falls on top of the subsequent one, and basically they sabotage each other, so they lower each other's power production. Okay, so this is a negative effect. Now, the good thing about these vertical axis wind turbines here is that when you cluster them, right, what happens is that the great synergistic phenomena where one essentially promotes the power production of the other by, because we have this, for example, counter-rotating motion. So this was relatively recently suggested from a research group in Caltech, where they found an order of magnitude higher efficiency of these vertical axis wind turbines, but per area. So we're talking about energy power production per area, energy density. So this is also one of the motivation, one of the research goals right now to check the synergistic phenomena in this kind of turbines. So after having said all of these design challenges, now the question is how do we characterize this, and how can we, measure them, quantify them, and inform, the industry. For that, we can, of course, go to numerical simulations. And this is something that is going on right now. It's an active topic of research, right? We are currently performing very large-scale simulations where we can put multiple wind turbines, and we can see the evolution of the flow field in the ensemble of the wind farm. Of course, the downside of this is that we're talking about extremely expensive and extremely complicated simulations. We are talking about wind turbines that can have a size of 200 meters, and we are talking about the small turbulent vortices or eddies that are of the order of maybe centimeters, right? So we are talking about billions and billions of degrees of freedom, and we need supercomputers to resolve these flow fields. So this is something that it's mostly for academic settings, and not it has not been used in industrial settings so far, this kind of fidelity simulations. Now, the other idea, of course, is that we can start doing experiments, right? This has been, of course, happening for decades now. But again, we have a challenge, especially when we are discussing very large-scale wind turbines, where we have these gigantic sizes and gigantic Reynolds numbers. So the question is, how do we fit this dynamic? How do we squeeze these dynamics inside the lab? Well, because in the lab we have miniature wind turbines, so how do we match the Reynolds number? How do we achieve dynamic similarity? Well, for that, we can construct specialized wind tunnels. So this is the wind tunnel that I designed in Princeton as part of this winter explosion that I was in. So the idea of this wind tunnel here is that it has pressurized air inside at 100 bar. And by doing that, you can increase the Reynolds number 100-fold, so you can start matching the Reynolds number of the wind turbine. Even if you have a miniature wind turbine, the Reynolds number that it experiences, the physics that it experiences, are those of 100 times larger, right? So this partially resolves that. Of course, this facility is extremely expensive and extremely time-consuming to operate. And well, we can say that we neglect this physics. We just go for what we can do: smaller wind turbines and conventional wind tunnels. This has also been done. This is a regular facility. But then again, this is quite time-consuming. It's quite expensive because when we have a whole wind farm or when we have an optimization problem, we might want to check hundreds or thousands of designs, right? And it's quite challenging to cover all this experimental envelope, right, using measurements. So then what data does the industry use right now if we cannot really rely on experiments, we cannot really rely on simulations? So what is predominantly happening right now is that we use semi-analytical models, right? And that run very fast. Of course, we reduce a bit the accuracy, but this is relatively good. And then we can run many cases and run optimization problems. And with that way, there are existing very popular, it's called blade element momentum theory models that calculate the power production of the turbines, or models that calculate the evolution of the wake velocities in the problem of planning the whole wind farm and where to position the turbines. Or, for example, there are blockage correction models where we are dealing with experimental measurements. And the basis of all these models that are basically what is the fundamental engineering tools that exist in the industry right now, in all the wind energy companies, is the so-called Rankine Froude theory. So this is a theory that initially started for propellers from the aeronautical applications. So it was called even air screw theory, because they were imagining the propeller as a screw that proceeds in the air. But it can be very well used for wind turbines as well, for the opposite problem. And the idea here is that we consider in a two-dimensional or symmetric problem a wind turbine that we idealize as a porous disk here. So simplification is of course very important. And then what we do is what we call in, and then essentially it's a potential flow problem, and they apply momentum and mass and energy balances here, and they can, one can get, it's quite simple actually to show. One can get the local flow properties and the forces, the thrust or the drag on this wind turbine. And actually, this is a comparison of the prediction of this theory, the solid line, with experimental measurements taken by Graham, which is an emeritus professor actually in the Department of Aeronautics. And you can see that this is the drag coefficient, so normalized drag, and this is the porosity factor, where zero porosity effectively is a completely solid disk, and porosity of 1 is a completely permeable disk, right? So we are somewhere in between for a wind turbine. And you can see that the theory is quite good for high porosities. It matches quite well. But then for low porosities, we have an increasing deviation to the point that here it's completely wrong. Now, of course, the theory is pathological from this point on, but this has not been a problem, until now or for the majority of the cases, because the bulk of the field wind turbines with the three blades that spin quite slowly, they are quite porous, right? So they are inside this region here. So they are quite easy, they're quite accurate to model. So the witness is happy, at least with this theory here. However, there are cases, especially now that we're talking about expanding wind energy to other applications. Well, we are discussing about how these vertical action turbines have these particular benefits of synergistic power consumption, or the micro wind turbines for urban settings that are extremely solid. But we have to expect to extend the envelope of operation to this region here. And then, this will create problems. And an example is this, not so recent anymore, paper from 2014, where these people, Pereira et al., applied the blade element momentum theory problem for different flows, for vertical action turbines. And here they increased the number of blades. This is just a normalized number. And here they increase the rotation of the wind turbine. So the most effective solidity is here on the upper right corner. And actually they concluded that this model failed when we went there, and they got completely unreasonable predictions, and they couldn't even present those. So we're talking about robustness, right? These models are not robust because at the point that we cross this limit here, then our whole theory will fail. So what we need to do is, if we want to model this region there, is actually, first of all, what I try to do, and this is something that I did as part of my postdoc, is try to extend this theory that is good for high porosity regimes to lower porosity regimes as well. So this is what I will present now, and actually to this theory for low porosity. Right. So a lot of a small thing of fundamental aerodynamics. I hope it's not too specific. So it is potential flow theory, the one we consider, so it's quite easy. So we consider a free stream that impinges on a distribution here of porosity that can be a wind turbine or a porous disk. Right, and the idea was first by the G.A. Taylor, who was a very famous aerodynamicist. It was in the 40s, this model here, where she considers this point vortices, and we can generate this kind of a wave structure. And then Taylor used the potential flow theory, it's called Lyell's theorem, the one used, to calculate the drag and the flow field inside around this distribution of porosity. And because the assumptions are quite the same as the ones that consider in the Rankine Froude theory, we have exactly the similar prediction as before. So it's the same problem, in other words. And of course, we see here that there is a problem here, a deviation with low porosity. And that means that at low porosities, this model fails. Some of the physics are not representative of what happens in reality. First effort of amending that, of improving that, came from Coe and James in the 70s, where they said that, look, this model is inconsistent because it has a momentum jump, right, a velocity jump. Because here we have to subtract the effect of the free stream to the effect of the sources, so we get u, the velocity u, but here they are superimposed, right? Because the source is an elementary fluid, let's say, element that expels fluid outwards. Okay, so we have a jumping velocity. This, of course, is not realistic. We cannot have, we have to have conservation of mass. So when James essentially imposed a conservation of mass across this layer here, this wind turbine here, and by multiplying everything by coefficient E, which imposes the boundary condition. Now, when James got another prediction, which was actually worse than one of Taylor, so I'm not plotting here, but I mean it was an effort, at least conceptually, in the right direction. Now, and then in 2018, what I proposed it was another deficiency of this theory. Now, the idea is that when we go to lower and lower and lower velocities, what happens is that we expect that the pressure here in the wake of the body to be lower than the ambient, than the atmosphere, for example, P infinity or P atmospheric. Whereas potential flow theory says, no, it has to be atmospheric. So this, of course, it's wrong. And what I did is I relaxed this assumption, and I allowed the pressure here to take an arbitrary value, PW, which I don't know what it is. But then I proceeded to calculate using the constraint of mass, momentum, and energy balances in a control volume. So some math here to do that. But then we have an analytical prediction of the drag coefficient, of the pressure coefficient of the wake, right? We have these predictions here. And this is the prediction of this analytical, it's an analytical study, right? And we have the red curve here, which behaves much better compared to Taylor. I mean, at high porosities, it matches, it's identical as expected, but at lower porosities, we behave much better. And actually, this solves our problem because the wind turbines we will consider, they will never be for porosities lower than 0.2, like 20%. Like wind turbines, even the most solid wind turbines, they will be around here, right? However, there was still a discrepancy between the prediction and the theory, unrelated, of course, to the application, but I decided to go the extra mile and try to understand what is happening, why, what am I missing in my modeling approach. And then we might remember from our basic aerodynamic studies that very solid bodies create a phenomenon that's called vortex shading, the shading of coherent vortices. But what they do is they lower the pressure even more, and they increase the drag of the object. When we go to high porosities, these vortices they do not appear, so we don't have to model them. But at low porosities, they exist. Now, of course, the model here is potential flow. It's quite simplistic. It cannot model this kind of very complex instabilities, right? So I listened and said, okay, it could be that. What I did is I put a splitter plate here, just a plate downstream, so that it inhibits the two shear layers here, as we call them, these two edges of the wave to communicate with each other, so they cannot really roll and create force. So basically, I killed vortex shedding and I remeasured the drag with the force sensor, and I found that it agreed with my theoretical prediction. So indeed, it's the vortex shedding that created this discrepancy from the theory, but until here we are good, and essentially no wind turbine will create this kind of vortex shedding structure. All right, so we are happy with the revision of this theory. It is quite significant in the sense that we can now take this result, this analytical result, and go to each and every of the engineering models that exist out there that use the old theory and substitute it for the new one, and see if we have any improvement for higher load turbines. So the first model that I will consider is the most popular way of predicting power for wind turbines. It's called BEM, or blade element momentum theory models, and I will apply that to vertical axis wind turbines. So a lot of things here. We don't have to pay attention to all of these things. It's just that this particular variant of BEM is called double multiple stream cube. Here we see the wind turbine from above, the vertical axis, so the blade goes like this. And the idea is that we basically divide the circumference of this circle into segments, and each of these segments is a porous disk in tandem, right? And we calculate for each of those the aerodynamic properties, and then we add everything. This is a simplistic approach, but it's being used in the industry. And the second part is the aerodynamic analysis, where essentially now we treat the blade, the rotating blade, and we take a data from tables, drag and lift coefficient that exist, from all the measurements. So the idea is that we solve this. There are a number of questions here, a number of questions here, and we solve them iteratively, end up with the result in the end. Now, the only thing that we have to keep from here is that in this momentum theory part, the old Rankine Froude theory is used. So what And this is work that I did with my colleague Anis Agati when I was in Princeton, is that we substituted the old theory with the new one that developed. So just a change of a few lines of code. So Anis downloaded the code from that is used in the industry. It's open source, and we revised it a bit. We changed some lines of code at least for the new analytic, to have the new prediction for vertical light turbines. Now, to validate this theory, we performed experimental validation. So what we did, we went to the wind tunnel. Now, we were lucky that in Princeton there was this high pressurized wind tunnel facility that can go up to 230 bar. So in fact, we increased the Reynolds number of the flow to a realistic value for a wind tunnel. So it's like we were testing in the field, essentially. So we could change here the Reynolds number. Lambda here is the tip speed ratio, how fast the turbine rotates, right? The Mach number of the flow, of course, we could not change. But we measured the power coefficient, so the normalized power. And this is the parameter space that we changed. An order of magnitude Reynolds number, a factor of 5 or so for the rotational speed. And we tested wind turbines of 2, 3, 4, and 5 blades, right? So these are the wind turbines we tested, and this is a count of the facility, of the section of the wind tunnel. Here is the vertical action turbine, and here is the measurement stack, right? So the torque sensor, the hysteresis brake to control the rotational speed, and there is a force balance for the process. All right. So for that, we could get actually, and these are the results. Now, what I plot here is a lot of graphs. Here I plot the power coefficient, the normalized power, versus the tip speed ratio, how fast the turbine rotates. Now, the symbols are the data that we got from the measurements, from the experiment, from the wind tunnel study. And then what we have is also the dashed line, that is the conventional BEM approach, but was the original model that we downloaded from the web. And the solid line is the new approach, the one that we developed with the new theory. And you can see that whether we, keep the Reynolds, change the Reynolds number, but we keep the blade number constant, or here, if we change, if we keep the Reynolds number constant, but we change the number of blades, the solid line is behaves much better compared to the dashed line for also cases, right? And actually, what is interesting is that at very low tip speeds, at very low rotational speeds, let's say, the two models are basically identical, right? And then they start diverging at higher and higher speeds, because the faster a turbine rotates, the more it resembles a solid plate or a solid disc, right? So the effective solidity increases. So this is where the new theory is accepted. It's actually, it shows the best improvement, one can say. So something that is, a nice, quite nice result from a theoretical result. We went to a more applied case and saw some improvement. But this is for the power, and now what I decided then to do is to try to apply this theory in another type of model that we used in the wind industry, and these are the so-called wake models that I have briefly mentioned before. Now, the idea is that we do not deal with a single wind turbine and the power output individually, right? But we deal with the whole wind farm. And as we discussed before, and we saw in this aerial photograph of the Werle, what happens is that the wake of the one wind turbine impinges on the other. So here I plot with, it's a contour plot of the free stream velocity of the wind speed. And you can see that just these are wind turbines here in the wind farm from above, it's a simulation in a sense. And downstream of the wind turbine, the flow flows from left to right. Downstream of the wind turbine, we have low velocity region. So it's very bad if a wind turbine is directly behind the wake of a preceding one, right? We lower a lot its acquired power. So the whole question now of wind farm planners is how do we position these wind turbines in an optimal way in order to maximize our power yield, right? So this is an ongoing question. It's a very hot topic right now. The thing is that what people use, they use this kind of analytical, either optimization method, they use this kind of analytical, semi-analytical models, wake models, right? And for example, this is Flores. It's a tool by the National Renewable Energy Laboratory, widely used. And this is wind farm. It's another tool. It has a similar thing. It's from DNV. It's a constant command. All right. So then the question is, how do we calculate? How do these models calculate the velocity here? And are they really valid for high load turbines? Can we do something better than what exists already? Well, all these models, what happens is that they treat each turbine individually, and they try to estimate the evolution of the velocity downstream of the turbine. So they start with the Rankine Froude theory here, close to the wind turbine, and then they use this as a boundary condition, and then this velocity evolves using the theory of self-preserving wakes, which I will not cover here. It's theory from it's a terminal theory. Now the problem with that is that both of those theories, the Rankine Froude and the self-preserving theory, treat the pressure as a constant, as the ambient atmospheric pressure, which we saw it's a quite good approximation for low loadings. But at high loadings, this is an approximation which is not quite close to what happens in reality. So what ideally we would need to do is relax here this assumption and make a new wake velocity evolution model where pressure evolves as well. All right. So this is something that I did with my colleague last year. So the idea of this model is that we have a wind turbine here, and we take a control volume here, the one that you can see, this by both sides. It's we're thinking about an axisymmetric problem, and we see the evolution of the wind velocity. This line here separates the wake of the wind turbine, the turbulent region, compared to the outer flow, where we have the outer velocity, which is unperturbed. And there is a communication, so the outer flow can penetrate here the wake flow with the mass flux M here. And this mass flux can be modeled using the entrainment analogy. First of it was initially the idea of J. Taylor and then expanded by Morton in the 60s. So the mass flux is modeled as such, is the velocity difference times an entrainment constant, which is an empirical constant, which is from experiments has been shown close to 0.1. Now, essentially, this is a parameterization of all the complex turbulent dynamics in a single equation. I mean, the accuracy, of course, would be better, but for the level of accuracy we are dealing here, it's, of course, acceptable. The other thing is that we need to model the momentum, right? So for that, we use the so-called classical momentum integral, right? So this is, again, given from turbulent theory. This is what is being used currently in analytical models. However, you can see here that in the evolution of the momentum, there is no pressure term. There is no. So what we did is we added here a pressure term, right? It can be given if you consider pressure can be shown to this will happen analytically. But the problem is that we don't know how to model it, right? We don't know how to estimate that. The pressure here is an unknown, and to estimate it, what we did is we considered another control volume, which is a donut control volume, which is encloses here the border of the wake, right? And we performed mass and momentum balance in this control volume here. And if you do that and you take a parameterization of turbulence from classical turbulence textbooks, you end up with this closure here. So this is the closure of the pressure term, which is until now has been not modeled, not considered in these settings of wind turbines. And you can see that it's a quadratic function of the velocity difference, outer minus inner, times the coefficient T, which parameterizes turbulence. All right. Now, the first thing we did is let's see how this fared with reality, right? Because this is a parameterization, it can be completely wrong. So what we did, we performed actually what my colleague did, performed larger simulations of wind turbines. So this is the pressure term that we want to model, and this is the distance from the turbine. The solid lines are the numerical data, right, that we acquired numerically using supercomputers. And the dashed line is the predictions of this formula here. And you can see that, I mean, of course, it is a very simplified representation of a very complex problem. but we are not far from what happens in reality. And for the accuracy that we consider in the wind energy application, it is quite accurate, at least after like 1 or 2 diameters downstream, which is the region that we are mostly interested in modeling. So we are quite confident that this produces relatively good results, and we can then try to solve this equation here, right? Try to integrate it. For that, as I said, the pressure comes from here. This is the thrust of the turbine, the drag. It comes from the revised Rankine Froude theory. So if we solve that, we expand it, we end up with this analytical model again, where u is the normalized velocity that we want to model, the evolution of the velocity here, and it's given as a function of the x distance. So essentially, we have now our analytical model that we can apply to this evolution of wave models that we considered before. So let's see how this fares again with numerical data. So for that, we consider the same larger simulations as we did before. So we consider the wind turbines, but we consider 3 cases, right? Where alpha here is called the induction factor, and it's actually showing, let's say, the solidity of the turbine. So low alphas mean very low solidities. High alphas mean very high solidities, right? Now, what I plot here is the evolution of the velocity as a function of the downstream distance from the turbine, which is positioned at 0, right? The black curves are the real, or let's say, the data that we will compare with, which is the simulation data, and the other, the blue curve is the analytical model that is currently used by wind farm companies, right? And the red one is the new one that we proposed in the recent article. Now you can see that for low solidity cases, the prediction, I mean, okay, it's not perfect, but it gives a representation that we can use. But the 2 predictions coincide absolutely, right? Because the 2 theories are exactly the same. There is no deficiency in the classical theory, at least that we can cover. So what we get, it collapses exactly with older models. However, when we go to larger and larger induction factors, larger solidities, you see that the blue curve underperforms greatly, right here at 0.4, and at 0.5, 0.6, the blue curve disappears because it gets negative or even imaginary values. Whereas our prediction remains quite close to what exists in even, someone would say, slightly even better. But the thing is that it persists and it's robust, right? No matter the loading of the turbine. Okay. Right. So this was the second model that I applied my theory. So the last one that I will talk today, it's called blockage correction models. Now, the idea is that we have at some point 2 measurements. We cannot get away just with analytical modeling, or we have to do simulations, and we get very valuable data. However, we have the contaminating effect of the walls, right? The walls do not exist in the field, but exist in a wind tunnel setting, right? As the wind comes here, we have the walls. And even in numerical simulations, we have the domain models, right? We have a limited numerical domain. We cannot expand it as much as we want because then the problem becomes extremely expensive. So the question is, what is the effect of this, the confinement effect of this numerical or experimental domain? So the effect is that what happens is that it accelerates, not artificially, it accelerates the flow, right? Because we think, for example, we impose in a wind tunnel a velocity of 10 meters per second, but because there is a confinement, the flow locally accelerates when it reaches the turbine and becomes more like 15 or 16 meters. So we think that we have prescribed 10 meters, but we prescribe something more. And then we have, like different measurements, right? So for instance, this is a recent study from Ross and Polaggi in the 2020, where they experimentally tested an axial flow turbine in 2 water channels, one very small and one very large, right? So the very small channel had a blockage ratio of 35%. So this is the disk area of the turbine divided by the cross-section of the wind channel in that case. And the very large water channel has a blockage of just 2%, so almost unconfined. And what they saw is that the very blocked case produced very high power outputs, right? Of course, because we have a local acceleration of the flow. And But this is artificial, right? Because then it's it can create the illusion of you have created a very efficient wind turbine, whatever. But in reality, when we go to testing in the field, you find something that is like 2 or 3 times lower. You know, so since we cannot have gigantic wind tunnels, what we need is effectively have a theory or a model that takes our measurements from here, right, and put it here. Right? We don't know the scale, but this is what we have to correct our measurements a posteriori. So there are lots of these kind of models out there, but all of them are quite similar. To be honest, their accuracy is quite similar, and because they are all based in the Rankine Froude theory, they have different names, but essentially their methodology and their conclusions are and the predictions are basically the same, right? So effectively, again, they treat the wind turbine here as a porous surface. Again, they perform mass and momentum balances in a domain, right? But now we have the effect of the wall. So the velocity here is not u infinity. We have the confinement effect. So it's a bit more. I mean, it's more complicated. It produces more complicated predictions, but in a sense, it's quite simplistic as it was before. Now, the problem is that, for example, in the case of the unconfined case, we saw that the drag coefficient is something like this, and we saw that this theory, this approach, the classical Rankine Froude approach, completely has wrong predictions at very low porosities. So this error will also continue, when we're trying to use this kind of theory, or even for the correction of blockages in the confined state. All right. So these blockage, in summary, these blockage correction models can be accurate here at high porosity turbines and not at low porosity turbines. So to amend that, what we did in a recent publication in 2022 is we considered we extended this theory for this novel Rankine Froude theory, but for a confined domain, for a confined where we have walls. I mean, very briefly, I would say that we have a potential flow theory again, and the question then becomes how do you create the effect of the appearance of walls in a potential flow domain? Well, this can be done using the method of images, right? So in this case, what we have to do is put in our potential for representation not just one plate, but a series of plates, right? This is just a mathematical approach, and if you put like infinite of those, then what you have is effectively you have the effect of split walls here. So it's like we have now walls that we can determine and regulate their size by regulating the distance between the different plates themselves. Now, if we solve, all of this problem analytically, the different momentum, mass, energy equations, we end up with this kind of extended prediction here for the drag coefficient, where you can see it has here the normalized velocity through the plate, and it has B, which is the blockage, right? Zero blockage, we return to the classical, to the prediction that I showed you at the start of the presentation for an infinite domain. So this is a consistent theory. But it's also a prediction for the velocity, the wave velocity here, the wave width, right? So we have all these predictions, and what I decided to do is take all these predictions and try to test them experimentally and numerically. So the first thing that we did is we performed particle image velocimetry here in a water channel in the round flume of Imperial. I tested different plates here, not wind turbines at this stage, just plates. And what we did is we tested here the force, the drag force on these plates, but also the velocities upstream and downstream to test the results of the theory. So these are some of the details of the experimental campaign. And then we also performed larger simulations of different types of turbines. So here it's slated for like a large scale wind turbine or urban size wind turbines in a sense. And these are the details of the numerical simulation of this wind turbine. Now these are flow fields. If we see the flow field from both downstream of the plate, so the flow goes like this. We have a high velocity region and the low velocity region behind the plate here. This is our investigation domain, and you can see here if we increase the size of the plates because we change the blockage of the plates to test the theory, you can see how the essentially the flow is squeezed and how the velocity here is increased. It's more red, right? Something similar happens here with the wind turbine. Here we have the wind turbine here, but then what we do, it's the opposite problem. We instead of increasing the wind turbine, we decrease the domain size, and you can see here that the shear decreases, right? So this is the flow as it goes downstream past the wind turbine. All right. So this is just the validation of our work, the experimental validation. So here I plot the drag coefficient versus the porosity of the plates that we tested, and the different lines correspond to different blockages. So this is a small plate and this is a very large plate, whereas the blockage channel, of course, remains the same. So this is the drag coefficient, this is the normalized velocity of the channel, and this is the normalized rate width. And you can see that in all cases, the theory predicts quite well. It matches the experiments. So we created a theory that is robust, even at very high porosity, very high loadings, very high velocities, and very high blockages. And now this is the numerical validation. It's essentially the real test of our model if we have really created a blockage model. So what this is from the numerical simulations of the wind turbine. So here I plot the normalized drag, and here I plot the normalized power versus the tip speed ratio, which is how fast the turbine rotates. Now, what we did is we performed the simulations at a very confined channel, as I showed before, and we got this power curve here, which is a solid line. And then we performed the same simulation, but in a much wider channel, which produced the blue curve here, right? Of course, as we expected, the power drops. And then the question is, can our model take the blue points and move them? The idea would be to move them exactly on the blue line. This would be an ideal model, okay? Now, I present two correction models here. The first is the one that's commonly used in the industry, in the literature now, the Werle method from here. And you can see it's the dotted lines, and our model is the dashed lines. Now, you can see that both models quite achieve in correcting the power. However, our model, the dashed lines, is more accurate, and effectively is more accurate at high tip speed ratios again, right? At low tip speed ratios, so at low effective, sorry, two correction models coincide. But as we go to higher and higher and higher tip speed ratios, our turbine becomes more and more solid, right? And then we can see really how the new analytical model predicts better the real power consumption of the turbine. All right, so this brings me just to the conclusions of my talk. So first of all, we discussed how there was a gap, at least in the modeling literature for wind turbines, where the high loaded turbines could not be modeled, and for that we created a revised Rankine Froude theory that can include high loading dynamics here. And then we applied this theory in three engineering applications. First, for the power prediction of vertical action turbines. Second, for the evolution of the velocity of horizontal action turbines. And third, for the blockage correction model of turbines and other love bodies. So yeah, these are the references for this talk. And special thanks to give special thanks to the group by Marcus Schultman that was working in Princeton, and these were the people that collaborated in this project. And here at Imperial, I collaborated with people with the very similar solution for the Imperial science. So yeah, thank you very much.
Are there any questions?
With high rotation, like solid, that's why there will be shedding effects. Could that have something to do with the wake lingering effect as well? Because the wake is also sort of doing that, and is that related, or is it just
right? I mean, the relation is not straightforward, let's say. I mean, actually, Elliot is investigating this right now in easy, and there is a connection there indeed. This is what we find. However, I mean, the wake meandering appears in cases at extremely high porous turbines that exist in the field, where there is no question that the vortex setting does not exist. As you make it more and more solid, we have found the body, this start of meandering becomes more and more upstream, and at some point it seems to transform into vortex shedding. So these two effects are connected, but this is not something straightforward or established, at least right now.
If there are no more questions.
I can ask one question. Okay, in the DEM model, where does the difference come from? Exactly. Not necessarily we're using like for the drag, we're using the correction from lower.
Ah, yeah.
Sorry, the empirical correction.
Yeah, okay. Yeah, okay.
What component is that makes the difference?
Yeah, no, you're right. I mean, what happens here is because the double multiples in approach. So the lower correction. So yeah, I mean, it's a very specialized question, this one. So the drag is predicted anyway well from the empirical lower correction. However, what we cannot get is the output velocity that the downstream disk receives. So for that, you need a new analytical model, right? Because there is no empirical correction. Lower correction does not yield.
It's the velocity.
It's the velocity, yeah. So if you didn't have the tandem approach, if you didn't have the downstream disk, then you wouldn't have it.
Thanks.
If there are no other questions.
All right, yeah.
Thanks.
Thank you very much.